So good morning class. Welcome to our class today. Now we're looking at chemistry and we're looking at a subtopic called electronic configuration, that is under the inorganic chemistry. Now when we define electronic configuration, we are describing the distribution of electrons within the orbital of an atom of the element. Now we have principles which are normally applied in assigning electrons within the atomic orbitals. Now the first principle is called Pauli exclusion principle. Now this principle states that only two electrons can occupy an atomic orbital. For example, when you look at hydrogen as only two electrons, and when you look at the position occupied by two electrons in the carbon, that is how they are assigned. So you can see a maximum of two electrons. Number two, we have the shielding effect. Now, this is how attractive the nucleus and the electrons are. So it describes how attractive the nucleus is to the electrons. Meaning that we must first fill those which are attracted first in our orbital. Our second principle is called Hund's rule. Now, in this principle, it says that the most stable arrangement of electrons is when they are in parallel spins. That's what defines what we call the Hund's rule. Then the last principle is called Aufbau or build-up principle. Now, this principle states that the protons are added one by one until we build up an atomic orbital. Now we want to look at how we can write various electron configuration of some elements. And I want us to do the one for lithium. Now lithium is a group 1A element. Lithium has 3 electrons. How do we write the configuration? Writing the configuration, we say it is 1s2, 2s1. Now there's something we need to know. For example, when we write the configuration, let me take this first quantum number 1s2. Now we look at 1 is the principal quantum number. The 2 is the number of electrons, whereas S is the angular momentum number of the element or the atomic orbital. Now, therefore, when writing the configuration of the lithium, we say 1s2 to s1. Now, this 2 is the number of electrons. This one is the number of electrons. Let's now look at another one. Another example is the one with the 4 electrons. That is, we can do the one for beryllium. Beryllium has 4 electrons. When writing the configuration, we will write as 1s2, 2s2. You can see 2 electrons in the first quantum, one principal quantum number, and also 2 in the second one. That's how we assign the configuration of the electrons. Now let us look how we can present again this particular electron configuration based on the atomic orbital diagrams we can do for each one of them. Let us begin with the one for lithium. We can say we have said it is 1s2, 1s2. So these electrons are written that way. Then this is 2s1, 1 electron, only 1 spin. You can see the first one, the 2 spins, and they must be parallel. That's how we apply the principle. Beryllium is 1s2, 2s2. When doing the diagram, the electrons are parallel, so we do it that way. We apply our principle in assigning the electrons. Okay. Now I want us to look at boron. Now boron has 5 electrons. Now in writing configuration, you write 1s2, 2s2, 2p1. Now you can see we introduce this quantum number 2p, okay? Because our atom has 5 electrons, that is 1s2, 2s2 and 2p1. Now in signing the configuration, we now introduce the principle that we had mentioned before, that is the ant rule. So we assign the first, the second and the third. So our first orbital is having 2 electrons which run parallel to each other, second the same, parallel to each other, and then we apply when we apply the ant rule, it applies here, you can see. So it must be like that. Now sometimes one of the ways in which you can also write the atomic orbitals, the configuration of the atomic orbitals, is by using, applying the Madelung's rule or Madelung's theory. Now Madelung's diagram look like this. We have 1s, 2s, 3s, 4s, 5s, 6s, 7s, or 2p, 3p, 5p, up to 6p. Then we have 3d, 4d, 5d, 6d, and then we have the last orbitals, which are 5f and 4f. Now, for example, I mentioned about lithium having 3 electrons. So we can see our first one is 1s, okay? Then second one is having 2, s1. Assume now we are writing, the Madelung theory actually shows the movement of the electrons, okay? Now, let me pick a one with many electrons. For example, let me pick carbon. Carbon has 6 electrons. We look at carbon, carbon is C. We look at carbon, it has 6 electrons, okay? Now carbon configuration will be 1s2, 2s2, 2p, 2p2. And when drawing the atomic orbital diagram, we say this is how it will look like. The spins might be parallel, and then these last 2. Now you can see that we are first assigning these last 2 electrons in the 2p orbital, this way, until they are filled is when we come back again. So what can help you understand the assigning of electrons in this orbital of the carbon is you can use the Madelung theory or the Madelung principle. We have said it has 6 electrons, so of course here we have 2 also here. So we are moving, first is 1s followed by 2s. Now you can see from 2s we have this way. So when we move this way, we come to 2p. When the 2p is full, normally p have a maximum of 6. When they are full, you come back again to 3s. 3 has a maximum of 2. When the 3s is full, we go to 3p. When 3p is full, we go to 3d. When 3d is full, normally d has a maximum of 8. When it is full, we come to 4s. Of course, you have said 4s, the s has 2 maximum. That's according to the first principle. 4p, p has a maximum of 6. Again, when 4p is full, we go to 5d. So, Madelung theory or principle can help you to assign electrons of the atoms. So you can do very many atoms. You can assign them their electrons in their orbitals. For example, let us do the one for fluorine. Fluorine is a group 7 element, that is the halogens. So it has fluorine has 9 electrons. Writing the configuration, all right? 1s2, 2s2, 2p6. Then as we had said according to Madelung, we now go to 3s. So you can see here we have, so it is, let's use our, it has 9, okay? Sorry, it has 9. Fluorine has 9 electrons. So here we have 2, those are 4. And then remaining 5, we put them here. A P must have a maximum of 5. This is the configuration of the electron configuration of the fluorine. Doing the orbital diagram, that is how we can do it. So we come here, the first 2. Okay, let's first fill that the first 3 first, because we apply the answer principle. You can see the P are 5. Let's do again. Now we can do it this way. Let's begin with the 1s2. 1s2, it has 2 maximum before we can go to P. We'll put it together. Then again the 2s. Then you can now do the P. Now the 2p, you can see there are 5 electrons. So as we were saying, we apply the Amps rule. So we fill this one this way first. Then we come back again, fill the remaining 2 that way. So we have 1s2, 2s2, 2p5. Let me do the one for sodium. We can do the one for sodium. Now sodium has 11 electrons. Again, sodium is a group 1A element, that's the alkali metals. Now, when we write the configuration for the sodium, we write 1s2, 2p6. Sorry, we move to 2s, okay? 2s2, then 2p6. Then how many electrons are those? Those ones are 10. So you can have the last one. We follow the Madelung's principle, Madelung's rule. The one remaining will hang there. So we have 2 plus 2 plus 4 plus 1, 11. Now we can assign these elements, these electrons, using the atomic orbital diagram again, as we said before. That is for the 1s2, and this one is for the 2s2, and this one is for the 2p6. Of course, we fill that way, then we come back again and refill. We fill each of the orbital, and then the remaining one, that is 1 electron. That is how we write the configuration for the sodium. Thank you.